Should I start? Okay, so thanks a lot for the invitation. It's a pleasure to be here. So what I'm going to talk is about a new result actually we got from the light sterile neutrinos. And first of all, let me mention that actually the idea of why we need a sterile neutrino, a EV sterile neutrino, is essentially because there was several anomalies that has been actually observed in the past. For instance, here we have the result of LSND, which is a very old story, where I access at lower energies, actually. And finally, actually, the most recent result, one of them actually that was also pointing to the sterile neutrino is the confirmation of the gallium anomaly. Although the gallium anomaly has been there for quite a long time, the recent result from BEST actually confirmed this anomaly. So in this scenario, actually, what we are going to do is just considering there are 4 massive states. Together with the 2 oscillation lengths that actually has been quite well measured already by experiment like a CAMLAN or atmospheric neutrino long baseline program, actually in this scenario we will have an additional one that will predict oscillation at very short distance. That's the one that actually we can see here. Here in this scenario, the 3+1, we will have 6 mixing angles that will correlate the flavor state with the 4 massive states. And also we will have 3 complex phases. And the idea is like we will, in this talk, we are going to review all the measurement that actually has been done trying to constrain this scenario, and we will see what are the results, what are the conclusions. So let me start actually by low energies, and the low energies actually what we have. In reactor experiment, what we have is just a huge flux of anti-electron neutrinos at the MeV scale. There are many different isotopes that can flux, but actually there are 2 of them that are quite, I mean, they are more important. This is the uranium-235 and the plutonium-238. And essentially, the measurement of this flux actually has shown that there are several anomalies that actually can, in principle, explain. The reason is once we have tried to explain these fluxes, actually with our model, we found several anomalies. Those anomalies can, in principle, be due to new physics, but also it can be due to the lack of our understanding of this reactor neutrino flux. One of them that actually has become quite popular is this bump that actually we found here at energies of the order of 5 MeV. This bump actually has been observed by many different experiments, and it's actually quite interesting because it's independent of the distance at which this flux has been measured. This is as an indication that actually it cannot be produced by a sterile neutrino because essentially it's independent of the baseline. But okay, also in the past, revaluation of the reactor neutrino flux. This is just the Huber-Muller determination of the flux, and they show also that there was some deficit once you make a comparison between the data versus the prediction of the flux, that there was some deficit in the observed data. And the uncertainty that they quote was of the order of 2%, and that gave us a tension, or what was called a reactor anomaly, on the order of 3 sigma with this with the current with. Now this anomaly again was independent of the neutrino baseline, but we had some results, and let me start mentioning, for instance, here the result of DIA, but it's not only from DIA, also we have the data from Reno and Stereo, and all those experiments managed to do was to make a comparison between the flux of the Huber-Muller flux and make a prediction between the flux as a function of the 2 main contributions of the 2 different isotopes, as you can see here. And it was very interesting actually because they saw that there was a very good agreement in the prediction of the flux with their measurement of the flux coming from the the plutonium-239, but actually it seems like most of the tension was coming from the uranium-235. And this actually was an indication that actually it might be possible that this reactor anomaly is not coming from a sterile or a BSN source, because actually it's associated to just one of the isotopes. So in case that is a sterile neutrino, actually the deficit or the deviation should be observed in all the isotopes. More recently has been new calculation of the reactor neutrino flux, as we can see in the right plot, and they have been able to compensate those those new calculations. Essentially, they include is the new ab initio calculation, but there are several of them, and they have been able to compensate and alleviate the tension that we have in the reactor anomaly. And this is one of the latest results that actually was published in Carlo Giunti paper. Now, this is not the only measurement that they have from a reactor. Also, we have some experiment like NEOS and DANCE that make a measurement at very short distance from the nuclear reactor. Let me mention that in the case of NEOS, what they are doing is just a measurement of the reactor neutrino flux at a distance of the order of 20 meters. And they compare the measurement. Initially, they compared the measurement with Diabase, although they were using the same nuclear reactor as in Reno. And finally, the latest result from NEOS is just a comparison of the measurement with the Reno reactor. The results actually have changed in the sense that now they predict a stronger bound over the mixing. But still, if you make an analysis of just of the data of NEOS, you will find always a preference for values of the mass that actually is different from zero. And the same actually happened from in the case of DANCE, which is a movable detector that is performed a measurement of the reactor neutrino flux with a distance between 10 meters and 12 meters. Here is the latest data, and actually, if you make an analysis, also you will find also a preference for a mass different from zero, also for a coupling also different from zero. Those are not the only reactor neutrino experiment that actually we have used, and also we have let me mention the information from the segmented detector. Those type of detector, they used just a small reactor, which is they have on the order of 50 to 80 megawatts. Those are the case of Stereo and Prospect. Those segmented detector, essentially they use a liquid scintillator doped with gadolinium or lithium, and they perform a measurement of the reactor neutrino flux at very short distance, which goes from order of 5 meters to order of 10 meters. It's very interesting, actually, the bounds that they got over the reactor, over the electron neutrino disappearance, over the sterile neutrinos, because actually they put a strong bounds, as we can see here. Yeah. Yes. Yeah, we included it. But actually, in this case, it's always actually a near far ratio. The 5 MeV band doesn't make a lot of things. Yes. Now, this is so far considering anti-electron neutrino or electron neutrino disappearance. But actually, there is another experiment that actually we have already mentioned that actually provides a lot of information about. And this is the case of the gallium experiment. Initially, gallium experiments were considered in order just to measure solar neutrinos. They were used for that. And actually, it was interesting because they were calibrated using radioactive sources, and this is the case of chromium and argon. And once they were calibrated, actually what they observed was some deficit. Now, more recently, the best experiment has also performed the same measurement, finding that also there is a huge deficit, and actually the result indicate that the deficit is on the order of 5 sigma. Now, this deficit actually, in principle, can be explained if you consider just that coupling of the new electron neutrinos with the sterile state. Now, the thing is, like those experiments, actually, as gallium, they don't have a huge sensitivity over the mass splitting, but still, they found, and this is the result that this is presented by this experiment, a preference for a mixing that should be actually quite large and masses that are larger than of the order of 1 eV squared. Now, we have performed a combined analysis between all the different electron neutrino disappearance, and this is the result that we have here, just considering only electron neutrino disappearance. The main interesting result is like a large mixing is preferred. The reason for that is essentially best. Best is the one that dominates this measurement and actually predict, or they need a large mixing between electron neutrino and the sterile. Now, there is another interesting aspect here, which is the fact that masses that are below 7 or 8 eV squared essentially are excluded. And the reason for that is just the combination of all the reactor experiment that actually we mentioned, and in particular is stereo, the one that I was showing you before, the one that actually they exclude this region, because I was mentioning before that if you make an analysis of all those experiments by each of them by separate, you will find a preference for a sterile neutrino, but they don't allow themselves. So once you combine all of them, you get that the EV solution of around 1 EV essentially is excluded. So reactor neutrinos essentially are pushing for large values of the mass square for the mass square of the sterile neutrino. Now, let's going to move to a different. No, doesn't kill. Actually, solar neutrinos is in tension here, and actually we'll put a strong bound. We'll put a strong bound here, but doesn't exclude completely. And actually, we include it. We include it at the end. Yes, at the end we include it. But the thing is, like once you include it, still you get a preference for the sterile case. I mean, for sure. Huh? I don't remember the value, but actually it was in tension. But yes, it still improved with respect to the null hypothesis, but I don't remember the value. I can check it. Yes. But yes, I mean it's in tension, but the thing is like the region is quite broad. Actually, let me show you. So essentially, even when the region is quite broad, this part is not completely excluded by solar experiment.
Since you have many degrees of freedom. Okay.
No.
No, I'm just saying, I'm questioning this, the value of global analysis, because with so big number of degrees of freedom, you can put in agreement everything. like Francesco started to ask what is kind of p-value of all.
At the end, I'm going to show you that there is no very good agreement. So that is going to be the message, but okay. Sure, you can put everything, but also it's the only way just to get a complete picture of the status. The only thing that we can do is just combine everything together. So yeah. Yes, that's what we are doing.
The point is to combine within a model and then wonder whether this model somehow is doing a good job,
sure.
Which is different from best fit. It's a statement of goodness of fit. It's
well,
another statistical problem.
The goodness of it actually will tell you whether there is a very good agreement between the data itself or not. And, and it's going to also give you information if there is one of the data that actually can be removed and the chi-square is going to improve or not.
Yeah, but you should make a statement whether this model is acceptable or
yes.
not.
I'm going to do that. I'm going to do that, yes. But yes, solar analysis is in tension, but it's not completely ruling out this possibility. So that's the measure. Okay, so LSND. LSND actually was the first experiment actually pointing to the possibility of EV sterile neutrino, because essentially they were used in a measurement of pion decay at rest and also muon decay at rest, but also they have some division of decay in flight, and they observe an excess of event of electron neutrinos that actually will be compatible with a mass of the order of EV squared. And this is the result that they got here. Now, this experiment actually was tested by minimum. And it's quite interesting because actually, the analysis of minimum, they didn't observe any excess. But as soon as they managed to go to lower energies, and when I mean the lower energies means of the order of a few hundreds of MeV, they observe an excess. Now, that excess actually has a preference for sure for sterile neutrinos. Actually, they cannot exclude the sterile neutrino, but as you can see here in the dashed line, this is the best fit that you will obtain with the minimum analysis, including neutrinos and antineutrinos, using just the prediction for the sterile neutrino. As you can see, you are able to compensate part of the excess, but you are not fully able to explain this excess. Here is this is in the left plot. In the right plot, what you will get is just the region that you will get. The region that you will get if you make an analysis of just of minimum, and you can see that actually they have a large preference for sterile neutrinos. If you combine with LSND, actually the preference go to more than 6 sigma. There was some other experiment that also tried to explore this possibility, but for instance, this is the case of Carmen or Opera, but they were not able to fully exclude the whole region here. Now, in the recent time, we have a new experiment that was microboom. And microboom was an experiment that was using booster neutrino beam. They measured, they use a new technology, which is liquid argon. They measured the neutrinos with a range that goes from hundreds of MeV to a few GeV. They use different samples, which is the case of CCQE with one electron, one proton. This is probably the cleanest channel that they have. Also, the pionless channel where they have just one electron, all the different, all the possible protons, and the inclusive channel where they include all the events with one electron. Actually, this inclusive channel is the most important one because it's the one that has a larger statistics. Now, one of the analyses that actually microboom has tried to do is just to see if they are able to exclude or not the mini-boom analysis. So what they did was they made an unfolding of the mini-boom excess, and they make a prediction for what should be observed in microboom. And this is what you observe here in this dashed line. So this is the prediction of what is the observed in mini-boom and how should it look like in microboom. And what they did essentially is like, fine, this is the excess. Now let's consider a normalization. And now let me explore what is the preferred normalization that we get in our measurement compared to the one that is the normalization predicted by, expected by minimum. And what they observe is essentially that this low energy excess actually is excluded to between 2 and 3 sigma, depending on whether you include the statistical or also the systematic uncertainties. Now, the thing is like this excess actually is not just an excess where you don't have any uncertainties related to the shapes. Actually, there are many uncertainties in this excess that actually can still be compatible with the minimum, but they are hard, or probably it's hard for microboom to be excluded. So this is one of the analyses that we did. Took all the backgrounds from minimum, we split it into different categories, and we consider different normalization for all of them. And that give us a different shape in the predicted excess by minimum. Therefore, this is actually what you can see here. This is 2 different examples of 2 different excesses that are compatible with the measurement from minimum. Taking that, we transform into what should be the prediction in in microboom, and this is what you have in the low energy in the lower plot. And then we explore what will be the goodness of what will be the agreement between the microboom and minimum to those 10 plates. And this is what you can see in the right plot. The color region is essentially giving you the p-value of those excess in minimum. And the vertical line essentially is the chi-square, the delta chi-square that you will get in microboom. So essentially, the right plot is telling you that it is possible still to get excesses that has a very large p-value in minimum, larger than, for instance, of 10%, that microboom won't be able to reduce it at the order of a delta chi-square of 4. So essentially, the significance actually drop a little bit if you include also the shape uncertainties in the minimum, in minimum excess. Nevertheless, actually, this measurement also can be used in order just to perform an analysis and a search of sterile neutrinos. And this is something that we also did. We considered this data and we explored. In this result, actually, what we were doing is just considering that all the background is independent of the sterile neutrinos. But actually, that has a problem. Well, let me first mention that just considering the different channel, which is the CCQE and the inclusive one, we were able to observe that a fraction of the minimum solution is essentially killed by microboom, but not completely. Now, as I was mentioning, actually, for this plot, actually, we consider that background, and what I mean by the background is essentially all the electron neutrinos and muon neutrinos were not affected by a sterile neutrino. But it doesn't make no sense, because actually, if you consider a sterile neutrino, also the muons can oscillate and can disappear, and also the electron neutrinos can also disappear. So actually, if you combine everything together and you make also an analysis of the background and consider that the background can oscillate, you will get a region like this one. And you can see that actually this is the minimum anomaly, or the minimum result after everything has been oscillated. And you can see that the result of micro is able to exclude a fraction of the minimum analysis, but not completely. Okay. Now let me move to the okay. Now we combine all the appearance results, and this is what we get. And this is actually quite interesting. We can see for sure that there is a preference for sterile neutrinos, but actually what is interesting is that the new result from micro essentially kill all the solution for large masses. So all the masses that are preferred are below 1 eV. And this is the combination of all the appearance results. And now let me move to the disappearance and disappearance result. And for the muon disappearance, actually, we have many different experiments. Let me start mentioning, for instance, the case of Minos, sorry. And Minos essentially they used huge flags of muon neutrinos with quite wide, broad in energy that go from a few, actually below the GeV scale, to 40 GeV, and they make the measurement in two different locations. At 1 kilometer away from the beam, and up to 700 kilometers from the detector. Looking for oscillation in the near detector or in the far detector, they were able to put a strong bound over the mass for the sterile neutrino. Actually, the bound is the strongest one that you will get. And essentially, for low masses, you will look for oscillation in the far detector, and you will make a comparison in the near one. Whereas for large masses, actually, you will get an oscillation in the near one, and you can make a comparison in the far detector. Let me mention also that this experiment actually is important for 3 neutrino oscillation, because they observe neutrino due to the 3 neutrino mixing due to the atmospheric mass splitting in the far detector. And this is one of the experiments that has and included in the global analysis. And finally, actually, let me go to the atmospheric neutrinos. Atmospheric neutrinos, essentially, they also have a huge source of muon neutrinos, also electrons. But if you consider just baselines that are just upgoing direction, the baselines are so large that all the oscillation introduced by 1 eV sterile neutrinos essentially is completely averaged out. Still, although you cannot have any sensitivity over the mass splitting, you can have some sensitivity over the mixing. And this is, for instance, these are the results from Super Kamiokande and IceCube. Essentially, in this case, is deep core. And they were able to put a bound over the mixing between nu taus and sterile neutrinos, and nu mu the sterile neutrinos. Essentially, nu mu, the coupling between nu mu and nu 4 will affect the normalization of the flags, and the coupling with nu tau and the new sterile essentially will modify the time independent. Here, I believe that those are the stronger bounds coming from u tau 4, actually. Although there was also analysis from NOVA also, but I think it was on this line. Now, if we go to higher energies in the atmospheric neutrino flags, of the order of the TeV scale, those atmospheric neutrinos essentially will predict a resonance behavior, because essentially now the oscillation length is comparable to the distance traveled by atmospheric neutrinos through the Earth. That resonance actually that you will predict here, the experiment that actually has been trying to constrain this measurement is IceCube. The latest result of IceCube, they have observed a preference for, it's just a 90% confidence level, they have observed a preference for a sterile neutrino with masses that actually are quite large. And those are the latest result by IceCube. Now, if we combine everything together, this is the result of the 3 neutrino mixing scenario. And as you can see, the main conclusion that we can get here is, first of all, we observe a preference for large mixings. The large mixing actually that we get is just essentially driven by best experiment, that actually they put actually they prefer a large mixing for the coupling between neutrinos and the electron neutrinos and the sterile one. Also, the other conclusion is like once you include the information from the reactor experiment, the solution that was allowed at the order of 1 eV squared moved, and actually now the preferred region is, I mean, now we have a preference for quite large, large masses, which is above 10 eV squared. Yes, I took a look. Actually, they were consistent. Actually, with deep core, which is able to also put a constraint in this mixing. I took a look, and they were in principle. I mean, they didn't observe anything, but they were not able to exclude this this part of the mixing. Yes. Yeah. Still is at 90%, so it's not a super strong preference. Actually, let me tell you something that actually the experiment that here has a strong problem is minus. Minus essentially exclude almost everything here. Okay, so this is what we, I mean, yeah, yeah, here it's just the effective mixing angle that you will get is UE4, 1 minus UE4 times UE4 squared, yes. So it's just essentially what we have is just UE4, coupling of parameterization of that, yeah. Actually, without times 4. Anyway. Okay, so this is great. Well, no, it's not great, but actually this is what we have. We have a preference for large mixing and actually large, very large masses. Okay. But as I was mentioning before, actually, we split all the discussion into in 3 different channels because essentially, although the preference for, in this particular scenario, there is a connection between all the different scenarios. If we observe an appearance in the result of LSND or minimum, it means that there must be a disappearance in some of the short baseline experiment. Otherwise, this scenario actually won't be consistent. So something that we did is just we make an analysis of all the different channels by separate. First of all, in 2018, what we found was like there was a huge tension between the appearance and the disappearance result. And this tension actually was essentially in the mixing. Appearance results prefer a very large mixing, as you can see here, whereas all the disappearance results prefer a very small mixing. Actually, they didn't find anything, and they were putting a very strong bound in the, essentially the tension was coming from the mixing. Now, with the new data, actually, the tension is not only in the mixing, but also is in the mass. As you can see here, for instance, the muon disappearance and the electron disappearance has a preference for very large masses above 7 or 8 electron volt squared, and the disappearance, the appearance result also has a preference for very low masses, masses below the EV squared, and that introduces a tension between the appearance and disappearance of the order of 5 sim. Yeah, we didn't include. Yes. That will be perfect. Not yes, exactly. No, I'm not happy. I mean, no. Hey. I'm making just a combination of all the experiment. I don't care if the sterile neutrino exists or not. I care, but okay. But what I'm making is just a combination of the experiment. I don't think the sterile neutrino exists. But anyway, no, I'm not happy. Well, also, I'm not. We are not including here because I don't understand essentially the result that they got. So okay. The tension here is interesting. It's essentially coming by because of a reactor experiment that they put a bound or they move all the appearance, all the disappearance result to very large masses, and also the tension appeared due to micro, because micro for all the appearance result essentially they kill all the large mass solution that actually before was allowed before micro. Now, we can try to explain this tension, and we thought on some possibilities. How we can try to solve the tension between appearance and disappearance result. One of them was the wave packet, actually. The idea here is like, so far, just considering plain wave, you will have a mixing between the neutrinos along all the propagation. And essentially, if you consider the neutrinos are it's just an object, so therefore must be a localized particle, so therefore they might have just a finite size. So therefore, if that's the case, actually, they can, after they propagate a very long distance, they should decouple one. I mean, the mixing should stop. And actually, we have some result of that. We have observed some incoherent fluxes of the incoherent flux of the neutrinos, as is in the case in the solar neutrinos on astrophysical sources. Now, how this decoherent effect will essentially manifest? Well, I mean, if we are able to observe that, they will damp the oscillation, just without including any, including any effect of the resolution of the detector. If you just consider the neutrinos are just a plane wave, the oscillation will be all the time. There will be all the time an oscillation. But now, if the coherence actually is comparable to the distance of the neutrinos they are propagating, essentially there will be a damp of the oscillation. Now the thing is like that coherence length essentially will depend on the size of the neutrino size. Now, there has been some calculations done actually by Alexei, and some people actually showing that actually the values for this decoherent length actually should be so large that actually we should not expect any effect in the experiment that we observed. Also, we have the result from Andre, from Valentina and Christophe, where they make an analysis of the Rino, Dayabey, and Camlan result, and finding a very strong bound in the size of the wave packet that should be the size of the neutrino, which is on the order of 10 to the minus 4 nanometer. And more recently, actually, the latest result from BEST, where they used beryllium-7, they used the recoil of the lithium after the decay of the beryllium-7 and the electron capture of the decay of the beryllium-7, they also put a very strong bound here. So actually, all these predictions tell us that actually we should not expect any observation of those wave packet effect in any of the experiment. We included this scenario in our analysis, and what we were found is like, sure, just considering this scenario, we were able to solve part of the tension. Essentially, the reason for here is that in this analysis, we include just the wave packet just in the reactor neutrinos. Essentially, what it's doing is just average out the solution at very low energies, making that masses of the order of the EV scale is compatible with all the disappearance results, and therefore part of the tension is reduced, but it's not completely. And actually, the tension is of the order of 3.5 sigma. You get a very improvement in the chi-square, but still you have a tension. This is not the only scenario that we consider. We also explore the possibility that the heavy state will decay. And in that case, they will also predict the coherence of the neutrinos. And in this case, in this scenario, we consider just the decay in all the different experiments. As you can see here is the prediction that you will get after you include the decay, and how they also introduce a different, in this case, is different compared to the previous scenario of the coherence of the neutrinos, and this is how the decay width will go. And once we include it, again, we get an improvement in the tension that we get. Actually, now the tension is reduced to 3.7 sigma, and now the decay allows to cover for the disappearance masses of the order of the EV squared. So now, as a conclusion, just let me mention that there was several attention that actually has predict, or several anomalies has predict the existence of a sterile neutrino. But actually the 3+1 scenario doesn't provide a satisfactory explanation. One possibility will be to explore several BSM scenarios. We considered 2 of them, but none of them were able to provide us a good description of the situation. And that's it. Thank you.
Okay. Yes, time for questions. Yeah.
Is there any bound on from the N-effective? So
yes, there are bounds, and from cosmology. I mean, from cosmology there are bounds, and actually all these masses essentially are completely ruled out. I mean, here we were. Yes, but also in that case, probably you have to consider a new BSM source in cosmology. That, for instance, that can alleviate the tension that you will get there with an effective. So far, we didn't include here any information from cosmology, neither Catherine. Also, these large values of masses also will be in tension with, well, actually with Catherine you will survive. But anyway, with cosmology you will be in tension, yes. But, yeah.
Which mechanism is your favorite one?
Whatever you prefer, but yes. No, I don't have any preference mechanism, no.
All this tension in this 3+1 analysis. But if we just limited the 3 analysis, I mean the standard model analysis,
Sure.
so we don't do any sterile neutrino, the tension between these same size.
Sorry, what do you mean?
The tension in this kind of groups of experiment.
I mean, in the 3 neutrino mixing scenario, you will not expect any oscillation in those experiments, in LSND or nothing like that.
You will not see anything,
No.
okay.
So
it's
actually,
not-
what we tell you in the 3 neutrino mixing scenario is like you have to explain these anomalies via doing anything else because they will not expect any oscillation. The oscillation length will be much larger than that.
It can be also that some of these experiments are wrong. So do you also have an analysis, I mean, like experiment by experiment, where you overlap all the alarm regions here, but considering single experiment, each one at a time?
Sorry, I don't...
I mean, here you put together all the experiments,
Sure.
no? But you could also do an analysis where you have one by one.
Sure.
So you can also overlap all the... Maybe some of these are wrong. I mean, some of these experiments
Yeah,
are
maybe
wrong, or you
one
don't
or maybe
consider
all of
that-
them are wrong, yes.
Yes, and then, I mean, if you would do like a plot where you have experiment, maybe you could find, for instance, a region where you explain everything, or still...
I mean, yes, if you do
Not
something
everything,
like
but
that, I mean, the closest thing will be something like this. But it shows you that actually, if you just make an analysis between appearance and disappearance, there is no overlap here.
No way.
Still, I mean, you can include it, and therefore you can get just some preference because there are some experiment that has a strong preference for that because they have a strong tension. This is the case of BEST. When you combine, they have such a large tension and deficit that once you combine with everything, they say, no, I prefer this and I don't care the other one. Yeah.
No way.
Okay, Thomas, yeah.
Thank you very much for the talk. I have many questions, but I will limit myself. The first one is regarding the results of Diabay, when you do or when you show the correlation plot between the plutonium and uranium, and you show that the anomaly or the problem mostly comes from uranium.
Yeah.
And I agree that it is a strong argument to say if it's neutrino oscillation, this should not be only on uranium. But on the other point, the different models were built on the same key ingredients, the fission yields and the nuclear databases. And I don't really get why it should be different between uranium and plutonium. So do you have an idea which ingredients in the spectrum is different between uranium and plutonium?
What's the difference between the combination of uranium contribution and the plutonium contribution?
No, maybe my question was fully asked. Sorry, I rephrased. In the prediction of the uranium and plutonium spectrum, they are based on the same ingredients.
Yeah, I don't know if it is based on the same ingredient. I don't know what are the details for those ingredient calculations, yes.
It's an intriguing question. I really don't have the answer. In fact, I was not alone, but I was one of the guys. I'm the head of the model. And I still don't know what was wrong in my calculation because I believe this is a strong experimental result which shows the calculation are problematic. But I don't get what's problematic in uranium which is not plutonium or...
Yeah, I don't know. I mean, you are the expert, so probably you can answer. You can answer.
No. Okay. And then a very naive question was, I think on slide 22,
Sure.
when you show the matter effect through the Earth.
Yes.
It's very, this one. Why do you say the resonance takes place for anti-neutrino? Is because you say M4 has to be very large? Why not for the neutrino?
I mean, there will be also, it might be possible that there is also a resonance for the neutrino channel. Things like in this case, when you include the sterile neutrino, you have to include the neutral current potential, because essentially neutrino doesn't have any interaction in the standard model, and that will move. But also it might be possible there is a, but you have a... Yes.
That's because of the constraint on the neutrino.
Please talk loudly so that everybody can listen.
So in this case, we don't do the same as in normal inverter and neutrino scenario where we flip the sign. In that case, but in this case, no, we are always looking for a heavy state that is there.
Andrea, you want to say something? No?
Olga?
If you do not make economy and make two sterile neutrinos, could you improve this?
Yes, okay, great. So the sterile neutrino has been explored. Yes, good point, because actually we have explored that and you don't get any improvement with two sterile neutrinos. And people even consider the case of three sterile neutrino and you don't get nothing. So, yeah. Olga.
I would just
Has in 2024 has a new limit and new release.
Sorry, I cannot hear you.
Catherine,
Yeah.
Catherine data can change this somehow. New measurements from Catherine.
Catherine essentially what it's going to do is put a strong bound over the high masses regime, and essentially they can all this part here. So yes.
Okay. But they have released new data, right? In neutrino.
Yes.
Have you tried to see what
I haven't still tried to take a look on that, but that will
okay,
be
so next paper, you know what you have
exactly, including Catherine.
So in the last slide, you talk of a standard model, say, effect. I will sort of suggest that it's not a standard model effect, because I mean, standard model is defined in terms of some fields, some gauge model, but I mean, sterile neutrino is not part of the standard model, and we should include it. So I would say that it's more important than somehow we admit to discuss motivation for this kind of things, because, I mean, this kind of results were known since 20 years. We already had global analysis, and we found a very similar situation with less significance. But why to insist so much? I mean, maybe we, as a theorist, we should do an assessment on why. I mean, one point is to explain data. This is one story. One point to have motivation for sterile neutrino. This is not that clear to me that we are discussing sufficiently.
But still, as you pointed, we have data, we have strong anomalies coming from many experiments, and I think it's important if we try to explain it. Looking for a modification of the experiment, actually there was a very nice paper from Vedran and Joachim Kopp trying to explain this tension coming from BEST, and they couldn't explain everything. Still, this data is going to be there, so it's better if we make an effort.
So probably I was not clear. So I don't say that it's not important to discuss data. It's important to discuss data, but the hypothesis that we are using to discuss data, sterile neutrino, is a specific one. Does not belong to a standard model. So before buying it, we better think whether we have good reasons to have something like this independently on the data that we want to explain. Otherwise, this is a circular argument. So this is kind of thing that probably we better discuss with more care.
Yeah, I agree.
Well, you can explain the difference of mixing in quark and lepton sector. So you see, just you can explain mixing or large mixing in lepton sector due to sterile neutrinos, of active neutrinos. Because mixing of sterile and active neutrinos modify the mass matrix of 3 active neutrinos. And it can modify in such a way that you will get large mixing, or maximal mixing. Due to presence of...
For that mixing with sterile neutrinos, you have to put something like X.
Well...
So it's not true.
No, this is interesting discussion. I mean, independently on the result. Yeah, it's important discussion.
It is. Yeah. Sergio.
I'm surprised you cannot explain this with 3+2, given that you have two
I mean,
two different mass scales.
Okay. Okay, let me mention that. It's not that you cannot explain, but you get more or less the same delta chi squared, the same improvement with 3+1, I believe. That actually you don't get.
You have very separate mass scales, which different disappearance and appearance
And we will expect it also because of the disappearance. Actually, the appearance actually can accommodate that. But if I remember correctly, from the global analysis, we include the 3+2, and we will get it essentially the same. But actually, I don't think we are even the first one finding that. I remember that there was some paper from Joachim Kopp, Michele, and so on and so forth, saying the same. 3+2 is nice, but it doesn't give you a huge improvement with respect to 3+1.
Didn't say it's nice.
Okay, I added that part, yes.
Maybe just a comment on the decoherence. There were some limits from the Diabe experiment. I don't know if you're aware of it. They couldn't find any effect from the decoherence.
The analysis is from Andre, so.
I don't know.
Actually, yes, Kamla is the one that put the strongest bound, actually.
Kamland.
Because it's the longest distance, so therefore you...
But already Diabe couldn't find any. Okay. Other comments? See?
It's just better a curiosity on a specific difference between mini boon and micro boon, no? I mean, micro boon, when they did their analysis, they did their analysis also trying to assume the same kind of backgrounds that was done in mini-boom. I mean, because maybe mini-boom made a wrong background estimate. So micro-boom, this also tried also the same wrong hypothesis, and in that case, they found nothing. I mean, no excess.
Yes.
Even with the wrong hypothesis of mini-boom. The same. So because my idea is that probably mini-boom, they have new software, so I am not sure. I have not checked the literature, but I want to know from you if they really tried the same hypothesis as before.
Yeah, they test the same background. The thing is, like for microboom, essentially, it's a detector that is able to make a better measurement in the low energy part. So therefore, for them, was like in principle easy just to identify what is the electron neutrino.
Okay.
And they they extrapolate all the background, all the excess. I mean, not all the background, but they extrapolate the excess compared to the background. So if still there are some problems in the minimum background, you don't know how they will affect it. But there are people who have explored the possibility of there is an error in minimum, and they were not able to find to compensate the whole excess.
Okay.
So
but
there are
even in case there is an error, I mean, there
you are
no excess.
No, even in the case that they don't find anything. That's what.
But there were on this low energy excess, there had been a lot of discussions on the problem of reconstructing the energy of the events and the fact that cross-sections, one was mis-evaluating it as a number of contributions, like the two-particle, two-hole. So maybe this has been corrected for it? I mean, this has been implemented in the...
It may be possible, but as far as I understand, the 2p2 hole actually will be very important at high energies, and the excess will be low in the low energy part where you will expect maybe CCQE interactions. I don't know if that will contribute a lot. It's true that there is a dependence, because actually you use the high energy part.
The energy reconstruction of the events.
Exactly. In particular, the high energy one, actually they will give you a lot of information for the reconstruction, for the fit, everything. It might be possible they have an effect, but...
I think it was also in the low energy part.
Okay.
Lower energy.
Okay, I'm not aware.
Okay, if there are no more questions or comments, let us thank Ivan again.